Welcome back to looking at the glorious topic of combinatorics. In this video we're going to be looking on arranging things, but having restrictions on those arrangements. And we're going to look at three cases. The case when we have some identical objects, and the case when we have some subgroups, and the case where we're arranging things in a circle. So let's start off when we have identical objects. Okay, so suppose what we're doing, we've got these letters. We've got A, B, C, and D. And we have to arrange these six letters in a row, in any way we want. So we've got 6 spaces, 1, 2, 3, 4, 5, 6 positions that they could go in. So here it would appear as though we have an n equals 6 for the 6 objects. We have r equals 6 for 6 positions. So we should be able to use the 6p6 formula of 6 factorial over 6 minus 6 factorial, which will just work out to be 6 factorial. It will look like that, but hang on, let's just do one of these possible arrangements. A, B, D, A, C, A. There's one of them. Just one of the many 6 factorial possibilities. But hang on, if I swapped this A with this A, wouldn't that give me the same thing? And wouldn't it be the same if I actually swapped this A with this A? So that and you know, other A's with other A's. So there are 3 A's, all of them could be swapped around. So there are 3 factorial ways of putting the 3 A's into those spots. So our 6 factorial options, that's more than what we should have. Okay, because we've forgotten about the ways we could swap our A's around. So we need to divide by 3 factorial. So answer is actually 6p6 divided by 3 factorial. So that's divided by 3 factorial divided by 3 factorial. Where the 3 factorial is the number of repeated, the number of identical objects. So for a bit of a formula, if we've got n objects, but let's use another symbol, p identical objects, then our permutations, our number of arrangements, is n factorial on p factorial. Okay, now let's think about an even weirder case. Imagine we've got, imagine we actually had this. We had A, B, C, D, 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 D. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 objects now. So this one would be 10 factorial, but how many identical objects do we have? Well, we've got 3 identical A's, so we're going to divide by 3 factorial. But we've got 2 identical B's, so that's another divide by 2 factorial. We've got just 1 C, so we don't need to worry about that. And 4 D's, so that's another 4 factorial being divided there. So it's the same thing, but you have more, divided by more sort of P's. So there's how you deal with that case, the case of identical objects. Okay, part 2 is thinking about subgroups. Okay, so what do I mean by subgroups? Well, I mean, within our arrangement, we want to specifically arrange some things next to each other in a little subgroup. So, for example, let's suppose we're arranging, types of cars. We've got a Ford, we've got a BMW, we've got a Mazda, we've got a a Holden, and we've got a That'll do, actually. Okay. Alright. So, suppose we've got these 4 cars, and we want to arrange them... If we wanted to arrange them in just any order, well, that would be easy. Any order, that would be 4 factorial, because there's 4 things. But let's put a restriction in. Let's say that the Ford must be next to the Holden. Who knows why, but let's just say. So Ford needs to be next to the Holden. Okay, there we go. So they need to be next to each other. So in a way, we've got a subgroup called the FH group. Okay, so that's like the Ford Holden is like a little group, and then we've also got, although these can be sort of swapped around within that, and we've also got the, whatever I said B was, BMW, and whatever I said M was, Mazda or something. So it's as though we've got 3 groups. So, there's this arrangement, or there's, there's the B, then the FH could be together there, group, the M, or could be swapped around or something like that. So it's as though we've only got 3 factorial ways of arranging these 3 things. But then, within this subgroup, it could be FH or it could be HF. They're still next to each other. So because of that, we need to multiply by 2 factorial to account for the way this subgroup can be arranged. So there's our answer, 3 factorial times 2 factorial. So let's try another example. Let's suppose that we had, I don't know, let's just do one with other letters. Let's say we've got A, B, C, D, E, and F. And let's say our subgroup has to be, so they are all going to be in a row, and A, B, C need to be together. They need to be together. So it's as though the A, B, C become their own group. Okay, that's their own group. So now it's like we've got 1, this is a group, and that's a group, that's a group. We've got 1, 2, 3, 4 groups here. Okay, so that's 4 factorial so far. All these groups can only be arranged in 1 way each, so that's fine. But this one could be arranged in 3 factorial ways. So there we go, that's the number of arrangements for that scenario. Okay, let's change the scenario a little bit. Let's say we've got the same letters, A, B, C, D, E, F. This time, A, B, C still have to be together, but also E, F need to be together. Okay, so now we've got A, B, C, that's like a group. D is a group by itself, and E and F is a group now. So we have 1, 2, 3 groups, 3 factorial. In this group, they have 3 factorial ways of arranging in that group. This is just a 1, so that's fine. And then this is a group of 2, so there's 2 factorial ways of arranging that group. So there's our answer. We'd multiply that out, and that would give us our answer there. Done. So if we want to sort of say it's sort of a general way, okay, so let's say we have n objects in m number of groups. Group sizes are, let's say group 1 is the size of the first group, so like 3 in this example was the first group size, and then group 2 is the size of the next one, all the way up to group M, which is the last group. So then, number of arrangements is m factorial. That's the number of groups. Like here, there we have 3 groups, 1, 2, 3, multiplied by however many are in the first group, g1 factorial, times however many are in the second group. In this case, there was a group of 1, so it's like a 1 factorial here, but 1 factorial is 1, so we don't bother with it. Times however many are in the third group, all the way up until your last group factorial. So there we go, that's just like this example there. So that's the subgroups. Okay, the third special case that we can have with our arrangements is if we're arranging things in a circle. So here we're doing arrangements in a circle. Okay, arrangements in a circle. So far we've only been doing arrangements in a straight line. So, for example, if we had Tim and Sam and Josh and, let's just have that. So we have 3 people standing in a line. Then there are 3 possible positions they could be in, which would give 3 factorial ways to get them into those positions. Now, the difference with a circle is, if we arrange these people in a circle, we have someone there, someone here, and someone here. So let's suppose that we put Tim here, and Sam here, and Josh there. That is actually no different to if we rotate this circle around and have Josh here, and Tim there, and Sam there. It's exactly the same, it's just that the whole thing has been shifted in a circular way, but it's the same arrangement. So in order to get different arrangements, we need to lock someone in position. So we need to lock someone into this top position. Once they're locked in, then it becomes like a line problem. So we can either have Josh and Sam in that way, or we could have the other option, swap them around. Now those are our only 2 options. So we only have 2 factorial ways to arrange this. Now suppose we have an extra person coming along. Let's say we have Alistair coming along. Now it's similar. We've got 4 positions though. 1, 2, 3, 4. But someone needs to be locked in here, and it doesn't matter who. So someone's locked in. So that position's all locked in. And now we've only got 3 positions left. So here we have 3 factorial ways of arranging. So in general, in a circle, with n objects, they can be arranged n minus 1 factorial ways. Okay, so here when we had 3 people, it was 2 factorial. Here when we had 4 people, there's 3 factorial ways. So it's n minus 1, whatever you have, take away 1, factorial. That's how many ways you can arrange objects in a circle.